Okay, so I'm going to give you an example of how to use Surfer in really a couple different ways. You should follow along with the video using the data in example site.xls. This is the same data file that we used during the last exercise where we first learned about Surfer. So the first thing we'll do is find out what the volume of the soil is above 580 feet in the map area. So to do this, you need to make a grid file of the topography, and this is a file, I think we called it elevation previously. So do that, and what that's going to be is a surface. If we were to take a cross section through the topography, we would have a surface like this. And we're going to do an operation in Surfer that calculates volume. And what it'll do is it'll take two surfaces, an upper surface and a lower surface. In this case, the upper surface will be topography, and the lower surface will just be the surface defined by 580 feet. So there won't actually be another grid file, although we could do it with two grid files as we've shown here. And when you do your homework problem, you will have two surfaces. But just to take a look at the nomenclature, this is in cross section, so this is the surface that we're starting with, and in the region where that surface is greater than the surface the second surface, that's called the positive volume or the cut volume. And where the first surface is below the second surface, it's the negative volume or a fill. And so the first question that we're asked is, what is the volume of soil above 580 feet? And the second question is down here, what is the planar area of the region of the site above 580 feet? So the planar area would be, if we were to flip this back to plan view, it would be the area that's defined by this region here. Okay, so let's go ahead and do that. We're going to switch over to Surfer, and here's the topographic surface, and 580 is right there. So the region above 580 is all of this region here. We want to find out about the volume as well as the area. So the way to do it is to go to grid, and if we've already created the grid, we go here to volume and we select the grid that we want to operate on. So this is what we're calling the upper surface, and this is kind of in quotes because the upper surface could in fact be below the lower surface, but this is the way we're defining the problem. So the lower surface I've already defined as 580 feet, and I hit OK, and it does the integration. And here's the results. So what we're interested in here are these cut and fill volumes. The positive volume is given here, and that's where the topography is above 580. There's the volume where the topography is below 580, and then this would actually be a negative volume, and if we add those two together with this being negative, then we get the net volume here, which you can see is a slightly negative number because there's more volume below 580 than above it. So this is the answer that we want. This is the volume, and we can just cut it out of here and go back to slide. So the positive volume, oops, just paste in there, and this has units of the well, this is the integral of the elevation over this surface area. And for our file, in this particular case, the elevation is in feet and the x and y coordinates are in feet, so the units of the integral are in cubic feet. So that's pretty easy. It won't always be that easy in terms of the units. Okay, so we want also to determine the area, and the positive planar area in this case is, there's 580, so it's this area, and that's given here, the planar area, the area of the cut, and that's the area, and this has units of whatever our x and y coordinate is. So in this case it's square feet. We can copy that over here, and that's feet squared. Okay, so that's pretty easy. We can just get the data right off of Surfer. So let's go to the next example where we have to do a little more calculation. And in this case we're going to use the same data file, and we assume the coordinates are in feet, the aquifer thickness is 10 meters, porosity is 0.25, and what we'll also assume is that the concentrations that are given are concentrations that have been averaged over the thickness of the aquifer. So they're averaged over this 10-meter thickness. So the first thing we need to do is make a map of the plume that includes a 2000 microgram per liter contour. And let's go ahead and do that. As it turns out, I guess right here I already did that. And we might want to, if we want to make that a little bit thicker, we could go and boost the thickness, and I labeled it right here, so there it shows up pretty well. And so what we're going to do is determine the mass in this contour, and the idea would be that this is really where the mass is elevated. The mass here below this 2000 microgram per liter is just at background. Okay, so we've done the grid file of this, and now we'll go back to volume, and we'll integrate the concentration file. And now we'll do 2000 as the cutoff. Okay, so we're going to look at this in just a second, but I think we need to have a quick look at what the calculation is going to be. So I'm going to go back to the slide, and well, I guess this is pretty straightforward. We need to have the planar area of the plume where the concentration exceeds background. So that's pretty easy. That's going to be the planar area where we use this 2000 as the lower cutoff, and so that's going to be what we need there, and we'll copy that, bring it over here to the slide. So that's so there's the result, and that's in square feet. And now what we need is to do the volume of contaminated water where concentrations are greater than the background. So this is the area in square feet, and the volume of contaminated water will be the planar area times the thickness of the aquifer times porosity. So we have the information from Surfer that we need. It's that many square feet times the thickness times porosity, and then this guy here is just to get the units to work out. So all these units are lengths total. So feet squared total cancels with feet squared total. There's meters cubed total, cancels with that, and we end up with cubic meters of water, that many cubic meters of water. Okay, so we've answered that question. Now, the next question is going to have us determine the total mass of contaminants in the region above background, and we need to do it in kilograms. So what you should do is also read over the notes, because the notes talk about doing the same kind of operation, and I pulled this graphic from the notes. This is a cross-section through the plume, and the surface is right here. And so what we've done is, with this 2,000 micrograms per liter, is put a surface like that. That would be the lower surface, which is constant. This surface S1 would be our concentration surface. And so what we need to determine the total mass is we need to get the region under here as well as this region here. So there are really two parts to this. We have to get the mass that's in this region, and basically you can think of this as the mass that we would remove to get the concentrations equal to 2,000 micrograms per liter in this whole region. And then this volume B, and again it's quotes, volume is in quotes, but volume B would be the mass that's within the 2,000 contour, that is really provided by water that is at 2,000 micrograms per liter. So this mass gets it all down to 2,000, and then this one accounts for the mass that is from the concentrations equal to 2,000. Okay, so we'll do this in two steps. The mass from A is the positive planar volume, where we're using concentrations and 2,000 times the thickness times porosity and conversion. So we go back to Surfer, and this integration has been done with the concentration surface and 2,000 as the lower cutoff. So there's the positive planar volume, and we take that, copy it over, and there's the result. And Surfer gives you these numbers that have many significant figures. That's really probably way too optimistic, so I've just rounded this to 1.59 times 10 to the 8th. And so the positive planar volume, what we've done here is integrated the concentration over the area. And so that has units of micrograms per liter times square feet. So this thing here, this number that we got from Surfer, even though it's called a positive planar volume, it has these fairly funny units. And that's one of the key things that we have to be on our toes about. And so the formula is that volume times the thickness times the porosity. There's thickness, there's porosity. And now we have to do the conversion, and this is really following along the same kinds of things that we've already done. Meters squared and square feet, the number of liters in a cubic meter. This is the number of grams in a microgram, and the number of grams in a kilogram. So you go through and everything is canceling out, and you end up with kilograms. So I would highly recommend, when you do this, that you write it out like this, and even go one step further than what I'm showing here, and for all of these lengths you write out whether, use the subscript about whether it's water or total, to make sure that those all cancel out properly. Okay, so 36.7 kilograms. This is the mass that we would have to, let's go back to Surfer here. So 36.7 kilograms, what that means is we would take that mass out of this region, and if we did that, we would have the average concentration in this region reduced to 2,000 micrograms per liter. So what we need to do is go back here, and to complete the analysis, we've got to go and let's see, go back to PowerPoint, and yeah. So we've got the 36. Now we've got to get the mass in B. So the mass that is within the contour that is provided by water that's at 2,000 micrograms per liter. So that's just going to be the area times the thickness porosity. This group of terms is the volume of water in that contour times the concentration. So the planar area, we already calculated that in the previous problem. That's this many square feet. The thickness is 10 meters. The porosity is here, and the concentration now is 2,000 micrograms per liter. And then we go through and do these conversions, and we come up with this value, 13 kilograms. So what we get is that it's about a third of the mass is from water that's less than 2,000 micrograms per liter, and this is from water that's greater than that concentration, or water that this is really the mass that's from concentrations above that value. Essentially, though, we have to keep in mind all of the water is above 2,000 micrograms per liter in this region. So the total mass then is the sum of these two, and it's 50.6 kilograms. Okay, so I guess one aspect of this, if we wanted to clean this water up and get it back down to background, and background was 2,000, then we would have to deal with this much mass. If we wanted to clean it up down to 0, it would be the total mass, that mass. Okay, so we also would want to determine what is the average concentration within this contour. So that's this last part. What's the average concentration in the region that's above the background? So the average concentration will just be the mass that we just calculated divided by the volume of the water. So we've already determined the information needed to do this calculation in these previous problems. So mass divided by the volume, and then what's really helpful is to get this concentration back into the concentrations of the original map. So I did some unit conversions here and got 7,400 micrograms per liter. Okay, so what I would recommend doing at this point is going back to the map, and let's see, we can take a look at this. Maybe it's going to be helpful just to blow this up. So 7,400. Well, here's 2,000, there's 10,000, so 7,400 is right in there. And yeah, you know, that seems like a reasonable value for the average concentration. One of the things that happens is that it's pretty easy to get messed up with units or make a mistake with the calculations. And so it's always a good idea to go back and just check and see if it makes sense. For example, if you did say you made a mistake with the units, instead of getting 7,400, you got 740. Okay, easy to make that mistake. Well, what you would find then is that the average concentration would be less than the 2,000. Well, all of the concentrations are greater than 2,000, so there's no way that that could be true. The maximum concentration is here's 35,000. So you know, the average, I mean, it makes sense that it's 7,400. So I would urge you to go and take a look at the problem and see if the values that you're getting. So the assignment for the lab is to go through and work out a problem that is a set of problems that are essentially the same problems that we've just seen, but with different numbers. They're just slightly different numbers. The cutoffs are a little bit different. So you'll get slightly different results, but I did that intentionally so you can follow through the calculations. You'll get a little bit different result, but it'll really be quite similar. And so go through, do those calculations, show your work, be very clear, and that'll be what I want you to hand in. I really want you to have a set of problems that you've worked through that are clearly done, that are correct, so you can use these for reference for further problems that you would work of this same type.